Welcome, my name is George Kadziolka. In this module, we will examine the process of debugging projects on a hardware target using Cross-Core Embedded Studio. In this module, we will start the debug process by going through the steps of creating and then launching a debug configuration. The target will be an ADSP BF609 dual-core platform using a JTAG ICE. We will get familiar with how to load and execute a program, including how to step through the code. We will then examine the debug perspective in more detail and the default views associated with it. Using a simple application, the basic debug operations that one would use on a regular basis will be demonstrated. Finally, we will take a look at some low-level debug views that can help facilitate the debug process. These will include views to examine disassembled code, CPU registers, and tracing. To start, we want to debug the application as a cross-core application. As pointed out in earlier modules, there are several ways of being able to select the same operation. The Debug As selection can be found in the Run pull-down menu, as an option next to the debug icon, or by right-clicking on a project. We can also simply click the debug icon. In any case, the Debug Configurations window opens up and the session wizard starts. For those familiar with Visual DSP++, this process is similar. First, a target processor is selected. The ADSP BF609 processor will be selected in this example. The next step is to select a connection type. If you are using an EasyKit through an attached debug agent, you would select the EasyKit Lite option. As I am using an HP USB ICE with the BF609 EasyKit, I will select an emulator connection. If you have a custom target platform with more than just one CPU in the JTAG scan path, you would need to define a new target with a target configurator. You would select a new platform and then edit it in the same manner as you would using the Visual DSP++. Make sure that all the devices in the JTAG scan path are declared in the correct order. For additional information on setting up a platform, you can search Target Configurator under Help. Finally, we select the platform from the list, which would include any custom platforms that we may have created. By default, there are several single CPU platforms available depending on which JTAG ICE one is communicating with. We then hit Finish to close the wizard. We are returned to the Debug Configurations window. The wizard chose a name for the configuration. We can change the name if we wish to something else, as I'm doing here. The wizard is also able to determine that we have a dual-core application and map the DXE file with its respective core. If there was a need to manually edit the programs to load onto a particular core, or any load options, we would select the entry for the core of interest and hit Edit. We can browse to the appropriate project and then select the appropriate DXE file. We may want to edit options associated with loading the program, such as disabling the Run Immediately After Load option if we want to debug the startup code, for example. I'm just going to cancel this to keep the original options. The Session tab is where most of the configuration setup takes place. There are other tabs of interest, such as automatic breakpoints. These breakpoints are set automatically after the program is loaded. It is possible to disable them by deselecting one or more. One tab you will likely use with a custom target is the Custom Board Support tab. When debugging a hardware target, customizations are enabled and a custom board support file provides reset values for several registers, typically those associated with the external memory controller. Additional information on setting up this XML file can be found by clicking on the Custom Board Support File link. The Multiprocessor Groups tab allows grouping cores into groups. The default group already has both cores in the Blackfin dual-core processor selected. As with the Multiprocessor Groups tab, you would rarely, if ever, need to change anything under the Source and Common tabs. You can get additional information on these tabs by selecting them and pressing the F1 key, or by searching Help. At this point, we could hit the Debug button to save the configuration and launch it. I will simply hit Apply to save the configuration file and then close the setup window. Next, we will look at launching the debug session. There are several ways of launching a debug session. We previously saw that we could have gone straight from the configuration setup window. We can select Debug from the Run pull-down menu. Pressing F5 will do the same. We can also press the debug icon, which is what I will do here. The project will be built if any changes were made since the last build. In fact, all open projects will be checked for changes. Clean builds will take place for all modified projects. This default behavior can be changed by unchecking the Build if required before launching option under the Windows pull-down menu after selecting Preferences, Run/Debug, Launching. A window will pop up as the debug session is launched. It asks if you want to switch to the debug perspective, as this perspective includes views that support application debug. Selecting Yes will cause the switch. If the Remember My Decision box is checked, then this window won't pop up every time a debug session is launched. The connection to the target is then established and the programs are loaded onto the two cores. Since our load settings included running the program immediately after load, both cores will start up. The debug perspective has several views that come up by default. The debug view shows the loaded executables, whether the program is running or suspended, and provides a means of controlling execution through a number of toolbar selections. The variables view shows local variables for the selected call stack. The breakpoints view shows the user-defined breakpoints in the system. The remaining views are ones that we have already seen, such as the editor view with the source files, the outline view, and the four views along the bottom, including the output console view. We will discuss these views in greater detail shortly. The debug view provides a number of controls for execution of code on the target. The resume icon enables execution. The suspend icon suspends execution. Step allows execution of one line of source code, including stepping into a function. Step over is similar to step into, except that a function will be executed completely rather than stepping through it. Step return will complete the execution within the present function and then suspend after returning to the calling function. Assembly step is similar to step, but executes one line of assembly code. We'll talk more about this later in this module. All of these icons we've discussed so far work on a selected core that is either Core 0 or Core 1, whichever one is in focus. The last four icons support multiprocessor debug. The multiprocessor group can be configured or set. By default, both cores are part of the multiprocessor group. We can resume the multiprocessor group, suspend it, or step the active group. A core reset will reset the selected core. Reset and reload will reload the last application. Finally, terminate will terminate the launch. Most of these controls are also accessible from the Run pull-down menu as well as hotkeys. In this example, the debug view is showing us that Core 0 is suspended at a breakpoint while Core 1 is still running. In a dual-core application, the startup code for Core 1 has a tight loop where it checks for a signal from Core 0 to enable it. We can step over the first few lines of code for Core 0 and see that once we get past the Core 1 enable function, that Core 1 hits an automatic breakpoint on entry to main and enters a suspended state. The Core 1 source file has been modified to also print hello from Core 1 when it executes. At this point, we can use the multiprocessor group resume icon to cause both cores to execute simultaneously. As we examine the console output window, we can see the printf outputs from both cores being displayed. We can try executing again by first reloading the previously loaded application by clicking on the Reset Reload icon. This time, we will just step through the Core 0 executable to the point where main exits back to the startup code. We can switch to the other core and let it run to the end by clicking the Resume icon. We'll reload a second time and simply run each core separately, and then terminate the debug launch. In this section, we will examine additional debug features and debug views in more detail. We will use a new application that performs several function calls from within a loop. We have already created a launch configuration for this application, so we will simply click the debug icon to launch it. We'll click the Yes button to switch to the debug perspective and then wait for the application to load. Rather than stepping through the first couple lines of code to the point where Core 1 is enabled, we could instead place a breakpoint at a line of code just after the enable function, or at the top of a for loop in this example. This is done by simply double-clicking on the gutter or the shaded area on the far left of the window. We can then run to the breakpoint. As we step into the loop, we see changes in the variables view. The yellow indicates that the variable value had changed. As we step further, we step into the fnc function first, and on stepping again, we enter the fnc2 function. The variable view changes as we switch from local variables in one function to those in another. The variable value is local to all three functions in this example. We also see the call stack in the debug view. Calling a function creates a new stack frame. The topmost frame is for the current function. We can see that by selecting different stack frames, we can observe the local variables contained within them. We can also see that the source window jumps to the function for the selected stack frame. After stepping back to the loop, we hit resume a couple times to let the code execute quickly before stopping at the breakpoint we inserted at the top of the loop. The Core 1 code also has a printf function that occurs in a loop. We will also insert a breakpoint at the top of this loop. Now when we hit the multiprocessor group resume button, both cores execute and then stop when they hit their respective breakpoints. Now that we have activity on both cores, it might be nice to see how the local variables look in each core. Most debug views can be pinned to a core by clicking on the pushpin icon. We see that this view is now pinned to core 0. We can then open up a second variables view, select core 1 in the debug view, and then pin the other variables view to core 1. Local variables in either core can now be examined by switching to the appropriate pinned view. Earlier, we saw how breakpoints could be inserted into the source file, with code execution suspending upon reaching the breakpoint. The breakpoints view allows us to see where in our project all of the user-defined breakpoints have been placed. Clicking on a line here brings up the source window to the location of that particular breakpoint. We can uncheck the box to disable the breakpoint. After disabling the two breakpoints that were inserted in this example, hitting the multiprocessor resume button will cause the code to continue executing without stopping. We can then either let the application run to completion or suspend it manually. There are a number of other debug views available. To access them, we select Show View from the Window pull-down menu. Additional views not listed here can be found by selecting Other. Let's take a look at the Expressions view. The Core 0 code has a couple of global variables, including a single integer called index and an integer vector called array. We can add index as a variable to watch. We can look at a particular element of array, specifically one less than the present value of index in this example. If we want to see the address of this element, we can precede the expression with an ampersand. We can also use an expression to view the contents of a memory location, in this case, the address we obtained of the element in the array. If we check the next sequential location in memory, we can confirm that the data is stored in little endian format. It is also possible to examine registers by typing a $sign ahead of the register name. In this case, we are looking at the value of the cycles counter register. Also, as with other debug windows, we can pin the expressions window to a particular core. When examining memory, another useful view is the memory browser view. We will select it from the Show View option in the Window pull-down menu. In the address line, we could enter either the number that represents the address in memory that we would like to examine, or we could also type the symbolic name of the variable we wish to look at. Alternatively, we can select the Browse feature and select a symbol to examine that way. In this case, we will display the contents of Array. We can scroll the window as well, in this case to confirm that the sixth entry matches what we see in the expressions window. The memory browser also allows one to fill memory with either a constant or with the contents of a data file. The data file format can be specified. One can also dump the contents of a section of memory to a file. The format can be in text or binary form. The area of memory can be manually specified by entering an address, account, and the step size. In addition, selecting a symbol with the browser will return the correct size of the entity, in this case an array of 128 integers. Multiple tabs are supported to monitor different areas of memory. Here we enter the symbol index and click on New Tab. We can see the value of 6 in memory as matching that in the expressions view. We can also pin a memory browser view to a particular core, as we are showing here. Another browser can then be opened up and pinned to the other core. We will display the array called Buffer in this view, and then pin the view to core 1. As we step through the code, or run to breakpoints as we are doing here, the changes in memory can be monitored through these views. Finally, we can change the format of the display by right-clicking the view and choosing from the format options listed. A data buffer can be viewed as a table of numbers in a memory browser. However, sometimes being able to look at data graphically can provide more useful information. A plot view will allow us to do this. After opening the plot view, we will click the Configure Plot icon to set up a new plot. There are several plot types to choose from, such as line, XY, surface, and contour. We will stay with the default line plot. We select a new plot. The next thing to do is to define one or more data sets to plot. We will plot the data buffer we call Array in this example. The dataset will be named Array. We can browse for the array symbol as we did with the memory browser. Notice the plot view recognizes the size and type of array. We click OK and move on. Plot settings allow us to set parameters to enhance the presentation of the data. We will select that a legend be displayed. We could choose names for the X and Y axes as well as selecting a logarithmic or linear data presentation. The Style option allows selecting colors, line, and data symbol types. The Process options allow processing the data on display with either FFT or logarithm as options, in addition to neither, which is the default we are selecting. After displaying the data, we can select an area to zoom in on. We can also pan and reset the zoom easily. Plot pull-down menu options include being able to copy, save, or print the image, as well as being able to export or save the plot settings and import or restore them at a later time. When debugging an application, there may be a desire at times to dive deep into the low levels of the application close to the CPU itself. This might include walking through assembly code or inspecting registers. We will look at both in this section. A disassembly view is not normally part of the default debug perspective, but will come up automatically when an assembly file is being debugged. For example, when a program runs to completion, you will see the disassembly view pop up and stop at libprog term. There is an automatic breakpoint at this location that causes the execution to suspend once we reach the end of the application. One can open a disassembly view by selecting it from the Show View option in the Window pull-down menu. The simple app we have been working with was just reloaded. We are stopped at the first line in main, which is a call to the ADI init components function. This call is seen in both the source file as well as in the disassembly view. I will also enable display of line numbers by right-clicking on the gutter and selecting Show Line Numbers. Next, we hit the Resume button to allow the Core 0 code to run until it hits the breakpoint at the top of the loop. Note that the disassembly window option to Show Source is enabled. This embeds the C source into this view. Execution has stopped at line 35 in the simple app core0.c source file. We can also see that the breakpoint in the source file which caused the execution to suspend is also visible in the disassembly window. In fact, additional breakpoints can be inserted in the disassembly window if desired. As we step through the code with the Step Into icon, we can see that we are advancing one source line at a time in the source window. In the disassembly window, we are jumping to the start of the assembly code that corresponds with a line number in the source file. If we switch to the assembly step icon, we see that we advance one assembly line at a time. The source file also tracks our progress, but at a slower pace since we are executing several assembly lines for every one source line of code. There are times where it may be desirable to examine register contents to confirm correct setup of a peripheral or to verify correct operation of an arithmetic algorithm. As with other views, we can select the Register Browser view from the Show View option under the Window pull-down menu. On selecting the New Tab option in the Register Browser view, a table of available registers to choose from comes up. As we scroll through the list, we can select from core registers such as pointers, data, and debug, as well as system registers including DMA, peripherals, and interrupt control. For this example, we will select the data register file. Note that by default, the values are displayed in hex. Right-clicking and choosing Select Format from the drop-down menu allows changing the data format to something else, like signed integer in this case. The format selected is valid for the entire tab group in a particular view. Here, we are opening a second view and relocating the view next to the first Register Browser view. The P registers will be selected for display. The default hex format is acceptable. As we step through the disassembled code, we see any changes in the register contents showing up with a yellow highlight. Here we are adding a second register tab to display the DAG or Data Address Generator registers. This view, as most other views, can also be pinned to a specific core if desired. Another view that can be useful in low-level debug is the trace view. This view allows us to take a historical look at code that had executed. After opening the view, we click on the Trace Settings button. For a Blackfin processor, just the cycle, PM address, and instruction columns need be enabled. Tracing is enabled by clicking the Start Tracing button. We have a breakpoint at the top of the loop that was inserted earlier. Clicking the Resume button will execute the code through one iteration of the loop. The trace view displays 2 rows of information per entry or cycle. The first is the address we were at when the branch occurred, and the second is the address we branched to. Branches could be the result of a jump, call, a return, loop, or an interrupt. Going through the history, we see branches to FNC1 and then FNC2, with returns from both. Hopefully you found this tutorial helpful. Thank you for watching.